So now we're going to talk about the fundamental theorem of calculus, part 2. And this is a very helpful piece of the theorem because it tells us that if you have a continuous function and you have any antiderivative of it, then when you do this integration here, when you take the integral from a to b, that is the same as doing f of b minus f of a, where this large f is the antiderivative. So it basically says, let's see. What this says is that we can evaluate a definite integral by finding an antiderivative and then evaluating it at the endpoints. That is what the fundamental theorem of calculus part 2 says. Now it doesn't say that the antiderivative exists, and it doesn't tell us how to find it. So it is helpful, but maybe not as helpful as it could be. So we'll take a look at some examples here, and we have the integral from 1 to 4 of, I'm going to rewrite this, x to the 1/2 dx. And then what we want to do is we want to remember basically about what we talked about doing section 3.9, which is the antiderivative of x to the 1/2 is adding 1 to the exponent and then dividing by that thing, and there's your antiderivative. So then what the fundamental theorem says is that the answer to this is simply placing those endpoints, f of b and minus f of a, into this antiderivative that we found and evaluating. So 4 and 1. And as we talked about before in the previous video, because we are talking about numbers here, this answer is going to be a number. It's a representation of area from 1 to 4. So we have 2/3, and then 4 to the 3/2 would be 4 to the 1/2, which is 2, and then 2 cubed, which is 8. And then, of course, 2/3 times 1 to the 3/2 is just 2/3. So we have this, you can write it out if you want, 16/3 minus 2/3. That's going to give you 14/3. And I mean, that's it. That's the answer for it. Typically, however, we use just slightly different notation. We don't like over here, I'm going to take my antiderivative, and then over here, I'm going to write it as f of b minus f of a. Typically, the way we would write it is doing a rewrite's never a bad idea. I am a big fan of the rewrite. But then typically what we would do is we would take that antiderivative, so 2/3 x to the 3/2, and then we would draw this line, which indicates our limits of integration, but we've already done the integration, so we're not using the integration sign. And I have from 1 to 4, so that's just telling what I'm integrating to and from. And then we put the values in, like we already did, and we'd have 16/3 minus 2/3, and then that's going to give us the 14/3. So that's typical. Some books may use something more like this. You might see that notation. Every once in a while you might see this notation, something like that. It just depends on the book and maybe video or something that you might be watching. So what this does is it allows me to continue to use the equal to sign, because I can't say that my antiderivative, my integral from 1 to 4 of the square root of x is this, because it's not just that, it's that evaluated. And so by doing what you see, what I have is I can continue to use those equal signs because everything that I have there is equal. Okay, so last page of this section. So in general, what this is just the antiderivative evaluated from a to b, and again, you might see it as something like this, but all of these big F, these capital F of x's, are the actual antiderivative. Yeah, just a lot of ways to say it. You could even see x equals a to x equals b. That would not be out of the realm of possibility. So just different notation that all mean the same thing. Now, anytime you're asked something like this, find the area, what it means is simply find the integral over the limits of integration that you're being given. So in a case like this, you would want to write the integral. And if you want, you can pause this and try to set it up. So setting it up would look like this. And then my next step, I don't need to rewrite it, would just be to take the antiderivative of each piece. Antiderivative of sine would be a negative cosine of x. Antiderivative of cosine would be sine of x. And then I'm going to write 0 to pi over 2, my limits of integration. Then what I'm going to do is use that fundamental theorem part 2. And I'm going to have negative cosine, we're always starting with b, pi over 2, and then sine of pi over 2. And then we're going to subtract, and I have two terms, so I'm going to use a big parenthesis here, a bracket. I have negative cosine 0 plus sine 0. And then I'm just evaluating what I get here. So cosine of pi over 2 is 0, sine of pi over 2 is 1, minus, and then we've got cosine of 0, which is 1, and so we have a negative on that, so a negative 1, and then sine of 0 is 0. So we get the answer of 2. Okay. So the area under is 2, and usually we would say, you might see the notation units squared because it is asking us for area. And so that would be, you know, if you think about a grid, that would be that it fills up 2 units squared. Sine x plus cosine x from 0 to pi over 2. Okay. Something to recognize is, although we're using x's here, you could have f of u du. You could have, you know, as we've already seen, you know, f of t dt. The point just there is that the variable inside is going to be the same as the differential on the outside, because that's what's telling us what to integrate with respect to, what variable to integrate with respect to. So let's take a look at a few examples. You are welcome to pause and try the rest of the problems on the page and see if you can get them. They're all the same using that fundamental theorem part 2. So you're welcome to try that and then check your answers, or just come along with me for the ride. So over time, and this is in Math 5A and Math 5B, you learn a lot of techniques for integration. But until you know those techniques, all you know how to do is take the antiderivative of pieces of a function, you know, separately. So in this case, in order to do this problem, we'd have to multiply out x cubed minus 1 squared. So we're going to have x to the 6th minus 2x cubed plus 1. And I'm going to put my parentheses and keep my differential there. And what that does is, again, it allows us to then take the antiderivative of each piece and then use our fundamental theorem part 2. So just using the rules for antiderivatives, I have the fourth and plus x. And remember, you can always, you know, look at your pieces there. If I take the derivative of, say, the middle piece, negative 1/2 x to the 4th, I'm going to have minus 2x to the 3rd, so that tells me that I did my antiderivative correctly. Antiderivative of any constant would be the constant times the variable x, and as you can see, that's what we have. And then we're integrating from 0 to 2, so all we're going to do is plug in our values and see what we get. I do not know what 2 to the 7th is off the top of my head. Is it 128? 2 to the 7th, yes, 128. So we have 128 over 7. We have minus 2 to the 4th. which is 16, divided by 2, which is 8, plus 2. And you'll notice in a case like this, when you subtract f of a, you're just plugging in 0 here, here, and here, and that's just 0. Well, I have 86 over 7. 86 over 7. For the next one down here, I am going to rewrite this. So notice that the one above and this one do require a rewrite, because you need to be able to separate your pieces. You cannot take the antiderivatives in the way that they are set up right now, these functions, because you can't, just like we have product rule and quotient rule, you can't just take the antiderivative of each piece and still have it like be divided. We don't have those rules and properties. So what I'm going to do is I'm going to rewrite my denominator as x to the 2/3, and then I'm going to divide each piece so that I have x to the 1/3 minus x to the negative 2/3. And what a lot of students do get confused on in the beginning, especially just in the beginning, is that they spend a lot of time, you know, you're going back and forth between doing some derivatives and doing some antiderivatives, and students do get confused on that. So it usually just takes some time to get used to it. So now I can actually take my antiderivative because I've got x to the 1/3 and x to the negative 2/3. And so I'm going to add 1, so I'm going to get x to the 4/3, dividing by 4/3, 3/4, multiplied by 3/4. Then we're going to add 1 to negative 2/3, which is so we're going to get positive 1/3, and then dividing by positive 1/3, we're going to get 3. Okay. What you will notice is I do not use the plus c. If I were to use the plus c, that c is going to simplify to 0 no matter what, because it would be in each piece, and then, you know, f of b and f of a, and then they would be subtracted and they'd be gone. So your definite integral will not use that value c, in case anyone's wondering. I do usually get that question. Okay, so from 1 to 8. So now we just need to evaluate. So we have 3/4, 8 to the 4/3 minus 3 times 8 to the 1/3, and then we're going to subtract what happens when we put in 1. So 3/4 x to the 4/3, and I mean, I do expect, especially now, the ability for students to show me kind of the work that's being done here. 4/3 times 1 to the 3/4 times 1 to the 4/3 minus 3 times 1 to the 1/3, and then we're just evaluating here. So 8 to the 4/3 is 2 to the 4th, which is 16. 16 times 3/4 is 12, and 8 to the 1/3 is 2 times 3 is 6. Look at this, and then I have 3/4, and then I have 3. So just simplifying that all together, you should get 8 and 1/4. And these are also things you can check. You could graph in Desmos x minus 1 over the square root of x squared cubed, cube root of x squared. You could put that in as f of x into Desmos, and you could see that from 1 to 8, do you get about 8 and 1/4 units squared? Because if you do, I mean, that's the idea. It's the area under that curve. It's just, unless it tells us area, our answer is just a number. We don't have to write that. Okay, so we're almost done. So now we have cosecant x, cotangent x dx. And in this case, you would just want to recognize that the antiderivative of cosecant cotangent is a negative cosecant. So I'm not rewriting here. I'm actually taking my antiderivative, because the derivative of cosecant is cosecant cotangent. And so because I have a positive cosecant, the derivative of cosecant is negative cosecant cotangent. So if I just have cosecant cotangent, then my original needs to be negative. So negative cosecant x, I'm going from pi over 3 to pi over 2. And then I'm just evaluating negative cosecant pi over 2 minus a negative cosecant pi over 3. And, think about what these values are. Make sure that you at least understand your unit circle enough to be able to say, yeah, my answer seems reasonable, looks correct. That's important. So cosecant is 1 over sine. So sine of pi over 2 is 1, and 1 over 1 is 1. So I have a -1 here, minus. And then cosecant of pi over 3 is 1 over sine of pi over 3. Sine of pi over 3 is root 3 over 2. So the reciprocal of that is 2 over root 3. And I mean, basically, we're just simplifying that. So depending on what you're being asked, this would be the exact answer here. That's just me combining it into one fraction. Or you can simplify it, depending on what you're being asked, here would be the decimal approximation. So just make sure to pay attention to how you're being asked to give the answer, because of course 0.1547 isn't exact. All right, last couple things. This is something we've really already seen earlier, but this idea is still saying if you were to integrate from a to a over some, the interval is a to a, that area is still going to be 0. That is not any different. And if f of x, big F of x, is any antiderivative of f, then for what you have above here, we want to just remember that, so I'm still using the line from above, that g of x is that antiderivative from a to x of f of t dt, that there are many, many antiderivatives. There's many, many things that can be an antiderivative of a function, but the only difference is that c, that constant. So it's just a reminder of that. And that is section 4.3.